Okay, so first things first, again, we'll refresh your memory a little bit about a relation here. So in math, okay, a relation is made up, okay, or what a relation does, okay, it's a pairing of elements of one set. In this case, we'll say like typically the domain. That's an example. Okay, so a good example of that, e.g., a good example there would be the domain. Okay, a pairing of elements of one set in like a domain with elements of another set. And typically, again, in Algebra 2, that's going to be a range. Okay. Doesn't have to be that, though. A relation is like a very, very generic, way to connect two things in math. Okay? Very kind of like plain, and not a lot of properties along with it. Okay? The majority of things that we study in math, or the majority of relations that we study, are more specifically functions. Okay? So we kind of like throw around that word function a lot, okay, and we kind of like use it so much that we forget that it has a meaning and that not everything is a function, right? And so we want to make sure, that we really use that word appropriately when we can. So a function is a type of relation. So it's like a more specific kind of relation. It's like one of those things where it's like every function is a relation, but not every relation is a function. So a function is a type of relation where each element, okay, of the domain is paired with how many elements of the range? One. That's right. With one element of the range. Okay. Type of relation where each element of the domain is paired with one element of the range. So there should be no number, no value in the domain that's paired with two different range values. That's the mathematical definition, right? You guys might have some different ways that you remembered, because you've had to do this in the past, I'm sure, where it's like, is this thing a function? Okay. So let's ask that question. Is it a function? Okay, and we'll do some examples here. So let's take a look at this table. Not very exciting table. 1, 2, 3, 4. And then is it a function? No. Yeah. Wait, huh? What is it? Is it a function? No? Yeah? No? Yeah? Confusing. All right, let me try another one here. Let's try another one. I'm not going to answer the question yet. Just going to blindly accept other people's answers.
I said no first, and then she said no. So.
Oh, so you feel encouraged.
Yeah.
I see. Is it a function? No. Which one? Number 2, number 1.
Number 2 isn't a function.
Number 2 is not a function.
The domain, the x values are paired with more than one y value. Number 1 is a function because the y value, no 2 x No one x value is paired with multiple y values.
Okay. We all agree with that? Are we convinced now? Okay. Let's try another one here. This is more fun this way, I guess. Okay, now I'm going to draw a graph. Is it a function? No, right? And like I don't know, for whatever reason, whenever I was like in high school, you know, when I was like learning math and stuff like that, this makes so much more sense to me. I'm like, yeah, no, clearly it's not a function, right? Because we have what test to help us figure out whether this is the graph is a function or not. We have the vertical line test, right? Okay. And specifically, what are we looking for the vertical line test? Anyone want to go ahead? Yeah.
If you draw a vertical line through an x point, there will be no two intersecting y coordinates.
Right. So for a vertical line test, right, we're looking for being able to draw a vertical line, and we only want that vertical line to intersect our graph at one point, right? If for it to be a function. So any vertical line you draw should only hit your graph at one point. But here, I drew a vertical line and it hits at 2 points. So can this thing be a function? No. Okay. Question. What do you gotta go get? Okay. And the vertical line test directly relates. The vertical line test directly relates to the definition of a function because this vertical line is all a single x value, right? The x value is not changing. We're not moving left or right. It's a vertical line, so it's all the same x value. This one x value has two different y values associated with it. In this case, right? Two of them. All right? So one x value, whatever this is right here in my x-axis, it goes to two different y values, so therefore not a function, right? And then back to this one, right? Yeah, it fails here at 1. 1 is paired with 3. 1 is paired with 1. So not a function. And then this one is okay. 1 is paired with 3. 4 is paired with 3. And so that can be like, whoa, what? But these are different x values here. Okay? And it's okay to be paired with different, the x values go different, the same y value. So yes, this is a function. Yes, yes, yes. Now, if I changed this point right here, instead of it going 1, 1, if I said 1, 3, would it now be a function? It's the same point, right? So that x value of 1 is associated with what y value? If I change this to 3, okay, right. At this point, this 1 would be associated with 3, and this same 1 is also associated with the same 3. So it would be a function. It would still be considered a function, okay? Because that one element, or that one element of the domain, 1, okay, is paired with only one element of the range. Just because the point happens twice, okay, it still follows the definition. Okay. But if you really feel strongly that it's not, I guess you could try and look it up and stuff like that. But I'm pretty sure if it's the same point, it's still a function. Pretty sure if it's the same exact point, it's still a function. Because it's still technically past that vertical line test. Anyway. All right, so that's function stuff. Okay, this is going to be more important to us as we get into inverses in a little bit, but I wanted to talk about even, odd, and neither first. Okay, so even functions versus odd functions versus neither. Okay. So even and odd functions are not mutually exhaustive. Like there's even functions, there's odd functions, and then there could be other functions that are just neither of those. Okay? So this kind of stuff will be on tomorrow's quiz. For sure, right here. Okay, so you want to make sure you got this stuff down here today. Okay, so even, odd, and then neither. All right, so first we'll draw an example, kind of like a, gosh, there's a good word for it, but I just can't think of it in my head. But anyway, like a exemplar, we'll say an exemplar. Okay, because of course there's many different even functions, but like the classic even function you might think of as the parabola. Okay, so f of x equals x squared. Okay, so this is just an example, right? This is not the only even function there is. It is an example. Okay. Odd functions. Well, a classic or a good exemplar of that would be cubic function. And then I'll get to the neater here in a second. Okay. So, even and odd functions, there's kind of two main ways to discern whether a function is even or odd. Okay. One is by looking at its graph and kind of like visually inspecting it, I guess. All right. So it has to do with symmetry. What kind of symmetry do we see here with this even function? What kind of symmetry do we see here? Think back to geometry. Yeah, Jen? Reflects across the y-axis. So there's a line of symmetry right here, okay? And you can take this piece of function, reflect it over, and it would match up perfectly. Likewise here, if you reflect it over the y-axis, boom, okay? So yes, that indicates that we have an even function, okay? So this is, we'll say line symmetry over the y-axis. Okay. So that's indicative of an even function. Okay, if you have line symmetry over the y-axis. What kind of symmetry do we have for this one? What's that?
Rotational.
Rotational, that's right. What kind of angle measure would we have to rotate?
180.
180 degrees. Exactly right, Eli. Yeah, okay. So we have rotational symmetry. Okay, over, or around, I should say. Okay. So rotational symmetry around the origin, 180 degrees, right? So you rotate my paper here around the origin. Okay, you see the same kind of graph, right? Perfect. Okay. So you're looking for that. Someone in block 2 said an alternative way to kind of like see the symmetry. Emma, did you have a different way you were going to say it?
I was going to say, looking at the sheet today, it's a reflection of the y and x-axis.
Okay, and Janet, what were you going to say?
Reflection of the origin.
Yeah, so reflection of the origin. I guess so. I think you can reflect through a point. I think it's something you can do. I'm not sure. I have to look at that. But yes, absolutely. The person block 2, another person block 2, yes, said that you could reflect over the x and the y-axis, and that would result in the same kind of deal. Mm-hmm. Yep. Okay. Yeah. Okay. So then, what would neither look like? Well, here are some neithers. Okay. So, and again, there's lots of options here. Okay. Why isn't this parabola that I drew right here an even function? This parabola was an even function. What's the difference here? Mm-hmm.
It's not over the y-axis.
Yeah, exactly. The line of symmetry. There is a line of symmetry. Okay, but Justin's exactly right. Okay, the line of symmetry is not the y-axis. So no. Okay, and then likewise here. I don't know. I can say like. Okay, something like that. Same kind of deal here, right? This cubic function, it does not have odd It's not odd, okay? Because the rotational symmetry would be like around this point. But for an odd function, you need to be rotational symmetry around the origin. Okay, it needs to rotate about the origin and have it. So again, this would be an example of something that's not. Okay. So what's like kind of what do we look for? Well, we just say it's neither if not even or not odd. It's just kind of a catch-all. Okay. There's one other way we can kind of like determine this too. Okay, and that is using algebra. So I'll show you this here, the algebraic way. Okay, so for an even function, if you take your function and you evaluate a negative x in the function, so if you do f of negative x, your result should be back to the original function f of x. Okay, so if you start with a function, okay, and you're asking yourself, I wonder if this function is even. Okay, you plug in negative x for all your x's, simplify it, and if it simplifies back to the original function, okay, then you know that your function's even. Okay, so let me do an example of that here real quick. Okay, so let's say we've got f of x equals negative 3x squared plus 4. Okay. F of x equals negative 3x squared plus 4. Well, let's visually inspect it here first, right? So if you want to graph it here, I'll put on my graphing calculator. If you want to get your graphing calculators out, feel free, or you can just follow along with me. Okay. So I'm just going to graph this. Let's just see what we should get here. Okay, let's see what we should get. So, looking at the picture, do you think it's going to be even? Yes or no? Yes? No? Yes? Okay. Anyone want to justify why? What's your thinking there? Okay, yeah, X, right? Symmetric over y-axis, right? We see that reflection, we could potentially do that, right? Visually. Let's see if the algebra supports it. All right, so again, what we're looking for here is I'm going to take that negative x, I'm going to substitute it in here. So, f of, and instead of just an x, I'm going to plug in a negative x. Okay. And so, this x right here will replace it with a negative x. Okay. Well, if I take negative x, that quantity, and I square it, what do I end up with? Positive x squared, right? Because what does it mean to square something? Multiply itself, right? So a negative x times a negative x is going to become positive x squared. I still have the negative 3 there, so this will equal negative 3x squared plus 4, which is exactly the same as our original function there. Okay? So check, it's even. Right? We can see that we result in the exact same function that we started with. Okay? So that's indicative of being even. We confirmed it, right? That's how we can confirm it algebraically. Okay? So now let's take a look at the odd version here. Actually, any questions on this so far? Sorry, I don't want to skip on too fast. Any questions? All good? Okay. So to find if it's odd or not, same kind of scenario. We're going to do f of negative x, but now we want our result to be negative f of x. Okay, so in other words, we're still going to plug in negative x, but now we want to see that our function is exactly the opposite of the original function. So here, when we plugged in negative x, we were looking to simplify back to the very same original function. Here, when I plug in negative x, my goal, I'm looking to see if our function is exactly the opposite of our original function. Okay? So again, we'll do an example here. All right, let's do f of x equals, make sure I get the right function written down here, 2x to the third minus 4x. Okay, let's inspect it visually just to make sure. Okay, now you might be like, Mr. Wood, I'm never going to do this algebraic method. I'm just going to graph it every time and just say the answer. Well, joke's on you if I ask you to do it algebraically and you only know how to graph it, then you're going to be stuck. Okay, so please make sure. I could ask you to do it algebraically, or I could put this on a non-calculator portion of an assessment. Now tomorrow you will be able to use a calculator on the quiz if you wish. It won't be super helpful. So, but in the future, right, I could put this on a non-calculator section, in which case you would need to be able to, show it algebraically. So just be aware of that. But since we're just learning it, I'll show you here. What do you say? Is it odd? Does it look odd? Yeah, right? Rotationalsymmetry.org. Let's do it. See if it works algebraically. Okay, so I'll plug in negative x. Oops, I'll do this with the colors again. Might be helpful. And messing things up. Okay. So all the x's are replaced with a negative x. And now we'll see what will result in. Okay? When you cube a negative x, so negative x times negative x times negative x, what's that result in? Negative x cubed, right? So we're going to have 2 negative x to the third, right? Minus, but it's negative x times negative 4, so that becomes a positive 4x right here. And that negative is times the 2, so you can make that negative 2x to the third plus 4x. Okay? So here I had 2x cubed, here I have negative 2x cubed. Here I had minus 4x, here I have plus 4x. Are these opposites? Yeah, right? If you want to see it even further, you can factor a negative 1 out, right? And so we have negative 1 in front times 2x to the third minus 4x. And then you can see they're exactly the opposite of each other. You can see that they're exact opposites. This one's the same as that one, except it's got a negative 1 in front of it. Okay. Okay, we'll do one more, a non-example here, which I'm like, there's a million non-examples we could do, I guess, but okay. Let's say we have f of x equals 2x to the third minus 3x squared minus 4x plus 4. Woo. So in this case, right, I'm putting it under neither. But what's our litmus test here? Well, for even or odd, you're plugging in a negative x. And we're trying to see what our result is. Okay? So the same thing here. The test we're going to use in a situation where we're not sure whether it's even or odd, we're still going to plug in a negative x. So f of... So replace all those variables, all those x's with negative x's. So that negative x cubed is going to become just a negative 2x to the third, right? The negative x squared will just become a positive x squared, so it says minus 3x squared. The negative 4 times negative x becomes positive 4x, and the plus 4, well, that's just kind of tagging along at the end there. Okay? Are these two results, or is this result the same as our original function? No. Are they exact opposites? No, right? These are opposites, but these are the same. These are opposites, but these are the same. And there's no way for us to manipulate this at all so that we either get this and this the exact opposites or this and this be the exact same. So in other words, it's just neither here. It's neither even nor odd. And if you graph it, you'll see it doesn't have the symmetry that we're looking for. Okay. Questions on any of that?
I have a question.
Yeah.
Why is the negative 3x to the second power, why is it negative? Shouldn't it be positive if you're multiplying the 3 by negative
Well,
plus 3?
So remember we started with a negative 3 in the front there. It's only the x that's being squared. Only the x is being squared.
Okay.
Right? So when I plug the negative x in to replace the x, only the negative x is being squared. So it's negative x times negative x, positive x squared, but then it's got that negative 3 that's multiplying with the negative 3x squared. Make sense?
Yeah.
Yeah, no, good. Good question. Thank you for clarifying, or getting asked for clarification. Okay, now I got one for you to try. Finally. Okay, so the question is even, odd, or neither? And here's the function. Okay. So yeah, question.
So, even function is just dominated per y-axis. Just any symmetry with y-axis. And then odd is just...
Correct. As long as you have reflection, like reflectional symmetry kind of thing over the y-axis, and then odd will
Always
be
going to be the one.
yes, all it has to be the y-axis.
And then odd is just rotation.
Rotational symmetry about the origin. So it has to be the origin, because you might be able to rotate other functions, like it's maximum up to each to itself. But it's got to be rotating about the origin. But of course, make sure you do the algebraic method too.
Yeah.
Yes, you can. You may not be. Oh. Okay. Question? So don't forget, you have where'd your square go? It does, but when you take negative x and you square it, right, it's negative x times negative x. So what is the result of negative x times negative x? It's not going to be just x. X squared. Okay, let's go to John. What do you say, John? Even. Okay, let's go to somebody else. See what they say. How about Alex? What do you say? Even, odd, or neither? Even. All right, one more here. All right, and then how about? I think Josh is he's out and getting some counseling right now, or getting some guidance right now. All right, how about Reagan? What do you say?
Said even.
Even, and it is even. Very good. Okay. So just real quick, right? We're going to plug in negative x here for all of our x values. Okay. And so we end up with 3 in the numerator, right? Negative x times negative x is positive x squared plus 2. And so we end up with the exact same result. Okay, so it is even. Okie doke. All right, so I handed you guys this inverses paper. Okay, this is actually printed out from your book. Okay, from the book. I'll let you guys go ahead and read through this and work on it some here. I'll take you about 5-10 minutes. Okay, front and back. Okay, just kind of like introduce yourself to this concept of inverses. All right. Yeah. So about 5 or 10 minutes, we'll go over this. Okay. And I'll just keep the video going, and people are watching the video, they can skip ahead 5 or 10 minutes until we go over it. But go ahead, read through this. Some of this might be familiar to you there. Okay. And we'll go over it together too. But I want you guys to kind of read through it there and try it on your own, see what you can remember.
Question about the one.
Yeah.
So there's 4 translations in that.
Mm-hmm.
Is the square or is there only 3 numbers?
Right. So the square root isn't. The way that we're kind of categorizing things, we're kind of keeping the parent function as a separate transformation that we won't. So yes, it's affecting things, right? But we keep the square root of x as like our main kind of shape, and then the transformations would be how we transform that shape left, right, up, down, stretch it vertically, or flip it, kind of thing.
Yes.
So the square root of x would not count as a transformation in that sense, then. If that makes
So then
sense.
which one for which?
So, like how do I know which one goes with
Yeah.
which you're saying? Okay, so let me get my warm up here. And you might want to write down the original functions, that way you can, clearly see too. So let me get this here for you. Okay. So there's the original right there. Okay, so now if you kind of look at this, and if you look at what's being described here, you might be able to associate some of them just from seeing some numbers there that match up. So yeah, that's your A value, A parameter. That affects both the fact that we're reflecting, because it's negative, and the vertical stretch by 3.
Okay,
Yep.
so it's doing buffering.
Correct.
Okay. I don't know if there's 2 different numbers.
Yep, it's kind of doing, well, and if you want to think of it as 2 different numbers, you could think of it as like, and then, square root of, if you want to. But we, obviously you'll never see it written like this. It'll always just be a negative 3, but yes. It's doing kind of double duty there. Okay? Any other questions, or are you good on there?
Good.
Good?
Oh, wait.
Guys,
Yeah, I have one question.
Yeah, well, go ahead.
So what is it, H? Yeah, H is always opposite. So
H is the number that's in with the x, so like this.
So when you're going down, would it be that you put it in there once, when you not put it in 5 to 6?
Okay, so repeat your question, sorry, one more time.
So this is H, but if you put it out here, because it's up and down.
So
you
then
gotta
when
put
it's
it in here,
outside,
so it's
when it's
plus.
outside, that's our K parameter.
Okay.
Because outside, that's a shifting up or down. When it's inside with the x, that's a shifting left or right. That's what H kind of helps to govern.
Oh, okay.
And H and K are just like, they're just like random letters that we happen to pick, and those are the ones we use, right? But the more important thing is the number that's in with the x, it affects left and right, because you think, right, x values shift left and right. And then when we do f of x, well now this is a y value, and we're going to move down 3 because we take that y value and subtract 3.
Okay.
So does that make sense there, the connection to the positions? But yes, this is the opposite of what you'd expect. You would go actually left 2, not right 2.
Okay.
But this one is what you'd expect to go down 3 with that. So again, please, as you're going through here, do try and answer these questions, okay? I try to identify, is this function 1-to-1, or is it many-to-1? And then is the inverse of the function also a function? Of course, you want to maybe complete your table here, okay? But this is using that same idea of function we just talked about at the beginning of the notes. Okay, and if you want to talk to me about something like this, where this 1-to-1 and many-to-1 stuff doesn't make sense, feel free to ask about that too. Okay, but do try and answer the questions. Exactly right. The inverse flips the domain of the range. It reverses relationship.
But I can't confront them, so I'll choose one or one.
Correct, because every one x value is paired with one y value, and then the same thing there, it's 1 to 1. Yep, it would be 1.
I'll say one.
Question. So I think it's like kind of like all together. It'll be the same answer for both. Okay? So you are right with this one. Okay, it is. Yes.
Or these are just over this what we see.
Yeah, exactly right. Yep.
Okay.
Mm-hmm. Right there, Ash. Okay. How did you determine this result? Right. So the idea of many to one means that there's many numbers, more than one number, attached to one other number, related to one other number. So do you see that happening? Are there many numbers that are attaching to only one number?
So it's not
Well, it's kind of both. So let me give you kind of this one. Correct. No. Right. So, well, they're different, right? So let me show you. This is an example of many to one. Okay, why? Because many, 1 and 4, are being mapped to 1. Many, 1 and 4, mapped to 2. That's many to 1. This is one number to one number, one number to one number, one number to one number, one number to one number.
If this was a positive 2, this is positive 2.
Okay, so then if it was, if this was both positive 2, then the negative 4 and 1 would both be positive 2, so that would be negative 1.
Okay.
Yes, the negatives matter, right? Because it makes it a different number now. Yes. Y'all doing okay over here so far? Yes. Right back here. Doing all right here? Questions? Yes. Yes, because you have these two that go to one. So many, more than one to one.
Okay, yeah. And which one is just one for each? Like it doesn't
Correct.
have
One x maps to one y, one x maps to one y, so on and so forth. All the way down.
Okay.
All right, let me get it. Generated right there. Yeah, I see, sorry. Yeah, exactly right. Yes, that's what should happen with the inverse there. Yep. So yeah, the domain maps to the range in F, and that range is then also the domain of the inverse, which then would map to the range from the original, or it would become the range, which is the original one's domain. So they flip-flop, right? Which is what you kind of saw right here, right? There to there to there, right? They kind of merge those two things there. So yep, that's the idea. Okay. Did you guys have questions? Sorry.
Yeah. So when is this kind of
Mm-hmm.
like one portfolio like this?
Mm-hmm.
That's not right. That's what.
Yes, because you have one x value, right? The one here. It's going to two different y values.
Yeah.
So you can imagine, when I think about graphing that, you have, like, let's say, here's the y-axis, here's the x-axis, right? You'd have 1, 1, but then 1, 3, right? They'd be like above each other. And so then vertical line would hit at both points, right?
So this one would be right then?
One, and yes, yep.
Okay. Thank you.
Yep, you're welcome. All right, question.
I thought of another.
Okay.
Yeah. The one.
Yeah, I know.
So anytime the A variable is a negative, it's doing two things.
Correct.
Okay.
Well, unless the A variable is a -1, in which case it's really doing just one, right? Because a -1 wouldn't stretch it.
Okay.
But yeah, for the most part. Yes, you can help here. Yeah, so this is really confusing. So you actually don't want to type in Oak Japan, type in your phone.
Yeah. Okay.
So you actually want to type in Frederick County Public Schools. there it is. And so then you'll just log in using your student ID, and you should be able to go from there. And then if you, when you need further help, I'll give you help with that too. Okay, one more minute here, and then we'll kind of go through this. Okay, inverses will not be on tomorrow's quiz. Inverses will not be on tomorrow's quiz. Okay. Inverses will not be on tomorrow's quiz. Hoping to finish this up after tomorrow's quiz. That's my goal. Okay. So let's just work through this here, or walk through this here real quick. Okay. Most of what I saw was pretty good here, so that's a good start. The majority of what we're going to be doing with inverse functions, work-wise, okay, is finding an inverse function, okay, or finding inverse of a given function. Okay. Sometimes the inverse function is not. Sometimes the inverse function is not a function, so it's just a relation, right? Inverse relation. Anyway, but we're going to be finding those inverses, and that'll be tomorrow after quiz, hopefully. Okay. Anyway, we already went through some of this, right? We talked about what a relation is, talked about what a function is, too. Okay, but one kind of new introduction is this vocabulary of one-to-one. Okay, and the nice thing is it's kind of a self-explanatory idea. Okay, what does one-to-one mean? It means that one element of the domain is paired with one element of the range, right? Yeah, so that's it, okay? One element to one element, okay? So so a function doesn't have to be one-to-one, because sometimes you could have two elements of the domain paired to one element of the range, right? That would still be a function, but it wouldn't be one-to-one anymore. That would be many-to-one, or I guess two-to-one. That's a big difference, okay? So if you see an output used more than once, right, that would be a many-to-one function. Okay, and we'll see what the importance of one-to-one is a little bit later. Or I might say it now. I forget. Anyway, so an inverse relation reverses the pairings of a relation. Okay, so it takes the x input and the y output, and it swaps them so that y is now the input, x is now the output. Okay, and the inverse of a function may or may not be a function itself. Okay, if the inverse of a function is also a function, it's called the inverse function, and it's written like this. Now, that can be a little confusing, because when we see something raised to the -1 power, you may remember, you might think that that was equal to 1 over f of x. Okay? But it is not. So put a little slash there for that equal sign. Okay? So f inverse of x, right, the inverse function of x, is not 1 over f of x. So Ms. Whitmire, 2 to the -1 is 1 over 2. 3 to the -1 is 1 over 3. X to the -1 is 1 over x. Why isn't this the same? And the answer is, I don't know, because they want to confuse you. Okay, because the math people that are in charge of making up math notation want to confuse you. Because I agree, this is the notation you would use for 1 over something, right? But no, it's the inverse functions. They are not the same thing. Be careful. Okay. All right. So let's talk about these inverses here. So the mapping diagrams show a function and its inverse. Complete the diagram for the inverse of the function. So -3 goes to what in the inverse? 0, right? Because 0 goes to -3. And then 2 goes to what? 1, because, again, the 1 went to the 2, right? So again, we're just swapping the 2. Okay, we swap the x and y. Swap the domain and the ranges. Okay? Is this function one-to-one or many-to-one? One-to-one. Okay? let's see here. How do I want to say this? 1x is paired with 1y. Okay? Is the inverse of the function also a function? Yes or no? Yes, it is, okay? Each x value in the inverse is paired with one y value. Okay? One y value. So if a function's 1-to-1, that means all of its x's and y's are, exactly paired 1x to 1y. So if we swap that, now every x will be paired with 1y as well, right? So in other words, if you start with a 1-to-1 function, you're going to end up with its inverse being 1-to-1. And so therefore, if a function's 1-to-1, its inverse will also always be 1-to-1, and will always be a function too. Right? If you start with a 1-to-1 function, then the inverse will also be 1-to-1, and you'll have a function as well. Let's look here. All right. Is this function 1-to-1 or many-to-1? Actually, I got it. Well, we'll just go ahead and answer that question first, since I'm there. Many-to-1, right? Because we have two x values paired with one y value there. So it's many-to-1. Okay. The x value of x values 1 and 4 are paired with 2. Okay, and then these blanks, let's see here, -3 would be 0 and 2 would be the 1 there. And now notice here, we go many-to-1, 1 and 4 both go to 2. Right? And then its inverse is the inverse of this function. Is the inverse also a function? No, it's not. Okay. X equals 2 is paired with more than one y value. Okay. So a many-to-1 function, its inverse ends up not being a function. A 1-to-1 function, its inverse ends up being a function. And yes, there is a general rule there we can follow. Okay. So, all right, that's as far as I got with my Block 2 class, so I'm not going to press us beyond that. But I do want to give you guys your assignment and also briefly touch on the topics that will be on tomorrow's quiz. I won't do this for every quiz, but since tomorrow's the first quiz and you're all like trying to feel me out, right? And see like, whoa, what's Mr. Whitmire going to ask? Am I going to fail this quiz? I have no idea. So I'll try and give you some ideas at least about what to expect for tomorrow's quiz. Okay? So let me stop my video here and then we'll go over that. And hopefully it doesn't crash.